This is the last video of the semester. Amazing. And what I will discuss are surface integrals, which are the equivalent of line integrals, but for surface, and just tell you where they enter in some fundamental theorem. Okay, so let's remember the Green's theorem. So Green's theorem is about vector field in the plane. So divergence and Stokes will be about vector fields in space, three-dimensional space. So what Green's theorem tells you, so there's two versions. So the first version is when you look at a curve C and you sum up all the components of the vector fields that are parallel, collinear with the curve, okay? So I'm sum F dot the velocity vector at the end of the day, okay? And the Green's theorem tells you that this is the same as summing all the curl of the vector field inside the region C, okay? And the curl, so it's in some sense it says that the curl captures the infinitesimal whirls of the vector field, and once you sum up all these whirls, what you pick up is the contribution at the boundary. Okay. And the other version is the divergence version, where you don't look at what is along the curve, but what flows out or in of the curve. And so it's again a line integral, except that you're summing the component of f now that is normal to the curve. This is the normal vector. Okay, so perpendicular to the velocity vector. And the theorem tells you that this is the same as actually summing all the divergence of the field inside. Okay, so divergence is about what flows in and out, and the curl is about what whirls. Very good. Now, what about vector fields in R3? Well, so there's two theorems that plays the same role as the one above. So there's the divergence theorem. And what it tells you is, well, if I actually sum all the divergence inside a region of space, and that region has to be closed, so think of it as a ball, for example. If I sum up all the divergence in my closed region in my ball, this is the same as actually doing an integral on the surface, okay? So what you're summing on the surface is the component of f, which is in the same direction as the normal vector. So it's what flows out or in, okay? This is the normal vector. So you want to sum up on all the surface, and that surface is the boundary of that closed region. So for a ball, that would be the sphere, okay? And this actually has a name. It's called the flux of f through the surface, okay? Now, one thing we don't know yet how to do, and that's what I want to explain here, is how to sum up, okay, on the surface. How can I sum these contributions? How can I integrate on the surface? Because that surface is curved. This is not like integrating on the region in the xy plane, which is flat. I have a curved surface. So it's going to be like integrating a curved line. So I have to slightly modify here the ds. And Stokes' theorem is similar in the sense that, well, I do have a surface, but now that surface actually is not closed. It has a boundary C. Okay? So it doesn't close on itself like a sphere. And what Stokes' theorem, which is the curl version, say is that, well, if I move along C, that border, okay, I move along C, and I sum all the contribution of F in the component of F in the direction of the curve, then this is like summing the curl of F, okay, in the direction of the normal vector. But what we're doing here again is a surface integral, that is, I want to integrate on that surface. Okay. Now I don't want you to know these theorems by heart, okay? But what I want you to realize is that we can compute all these things now with all the tools we have and verify the theorem if we want. Because this is a triple integral, I know how to do that. This is a surface integral, I'll explain to you how to do it, but it's just, at the end of the day, like computing a double integral. Here I'm going to have a surface integral, so at the end of the day it's going to be like a double integral, and this is a line integral. We know how to do this, okay? All right, so how do we do a surface integral? So it's good to go back to line integrals, okay? So what is a line integral? So what we wanted to do in a line integral is you have a curve, right, in space or in the plane, and I want to sum a function, okay, along that curve, the value of a function along that curve. So the simplest case we took was when f, this function, was 1, we were actually summing all the small segments and getting the length. When we were computing the line integral for a vector field, what we were summing is either the component in the direction of the curve or normal to it, okay? But at the end of the day, we were always summing a function along that curve. And the important thing was the element ds, the arc length, okay? And the arc length was what? Well, it's like Pythagoras, right? So I want the length of that segment, a small segment, but that segment is not necessarily straight, right? It has a certain slope, and so the length of ds is dx squared plus dy squared square root, okay? So if I parameterize my curve by x, then x as a function of the parameter is just x, so I get 1 here plus the derivative of y with respect to x square root of that dx. That's my element ds if I parameterize my curve by x. More generally, this is the size of the velocity vector, where the parameter now is t, okay, x prime square t plus y prime square t square root, and there's a dt, okay? So that gives you, if you want, the length of a small segment along the curve, okay? And that curve is curvy. It's not necessarily straight, so that's why we need this, okay? Now, surface integral, we want to do the same thing, but for surface, okay? And so here's a good question that we will be able to answer in a minute. It's a tough question. What's the area of the paraboloid 1 minus x squared minus y squared lying above the xy plane? Okay, so at the end of the day, we want the area of that cap. But that surface is curvy. How can I get the area? And a naive guess would be, well, I'm going to integrate my functions dx dy. But if you think about that, when you do this, you're actually going to get the volume. So it's not what I want to sum up. I don't want to sum f times dx dy here. What I want is sum all those little orange squares that are curvy. But what is the area of these orange squares? Well, it's a bit like the same question here. What is the length of ds? Okay? So how can I get the small area of these squares, these squares at each point? Okay? Well, the idea is to say, well, if I move in dx direction, a small amount dx in the x direction, and a small amount dy in the y direction, okay, what is the area of the square of the surface lying above these points x, y? And so we have to remember that a key tool is the cross product here, because the cross product gives you the area defined by of the parallelogram defined by two vectors. So what are the vectors that are relevant here? Well, it's the vector that tells me by the direction of that curved square, okay, of that slanted square. So if I move dx in the x direction, then I'm going to go up by how much? By the partial derivative of x, of f with respect to x dx. That's the definition of the partial derivative, right? How much the height changes if I move dx. Okay, so that gives me, if you want, the slant, the slope or that element ds, but in the x direction. Now I want that vector also in the y direction, so it's similar, and here it should be k. All right? And now what I have to do is the cross product between these two vectors. So this is what I do here. And what you get is this vector, minus del xf dx dy, minus del yf dx dy, dx dy. And the area of the parallelogram is the norm of that vector. So what I get is 1 plus dxf squared plus dyf squared. And then I can take dx dy out because it's everywhere. And this is what I have. So this is the element ds. This gives me the area of the vector, the area of the square, slanted square at the point xy. Okay, so it's dx dy, but times this factor that takes into account that the square is slanted. If the square is not slanted, it's flat, then I'm just going to get 1, because if it's flat, as we know, these derivatives are 0, so I recover dx dy. But if it's slanted, okay, the area depends on f. Okay, so go back to the question, and you'll see it's a very easy question now. And that was not the case before calculus. Now, if I want the area of that cap, what I want to do is sum all these ds. So sum, at the end of the day, the area of all these squares. Okay, so I know now that my ds is this factor, dx dy. So now what I have is a double integral. So we know how to do that, right? Chapter 14. Now in this case, the paraboloid, the partial derivative are this. So the function I have to integrate is 1 plus 4x squared plus 4y squared square root. Okay, now I just upload, right, my program to compute double integral. So first thing I have to do the picture of the region. So what xy do I have to integrate? If you think about it, is in the xy plane is everything inside the unit circle, okay? Because the intersection between the plane and the cap, the paraboloid, is 0 equals 1 minus x squared minus y squared, so it's the unit circle. So I have to integrate everything in the unit circle. And now there's a couple of red flags. Circle, x squared plus y squared. So I have to go polar. Okay? So the bounds for polar are all the angles to circle, and from 0 to 1, because, well, it's actually a disk, so I have to integrate all the radius between 0 to 1. Okay? And so this is the integral you get. And then you can integrate this really easily, because now dx dy is r dr d theta. Don't forget. Okay? And so there's an easy u substitution, and at the end of the day you get this, which is 5.33. Okay? And one thing to realize is that the area of this is 5.33. It is more than the area of the unit circle, which is pi. Okay, pi is smaller than 5.33, which makes sense because the area of this curvy thing has to be bigger because it's curvy, right? Bigger than the unit circle underneath it, right? So that's surface integral. We'll practice that a little bit in class. That's to review double integrals at the same time, okay? Thank you for listening during this semester, and I'll see you in class.